basically working with file system and storage for the last couple of years. And I did previously writing Linux FileSystem4Fun. I think it was in May. So that this is a continuation of this talk. For those of you who are not attending the previous talk, in the previous talk we basically talk about main structures in file systems. So we go through stuff like superblock, inodes, some simple operations like read, write, do mount for the file system. Also, what else we did? MKFS. So we were able to create the file system. We talk about the history and some design decisions, how file systems were created. But something that was not covered during this talk was the part how the file system works with virtual memory. So this important part was missing because of the time. So in this part 2, I would like to talk a little bit about pages and virtual memory. This will be like not talk which is focusing on virtual memory, because virtual memory, as you already know, is really complex topic and will require a few other presentations. But I will bring some basics and talk what from file system perspective is important and what from performance perspective is important. All right. So I would like on this talk. So first of all, just about the motivation of this talk, and then we will move to main concept. I will bring also a bit of history, VM as a start of the journey, and then some primitives like paging, swapping, some easy mechanisms of managing the virtual memory, which also are important from the file system point of view. Then we will go to the caching and latencies, because all modern computing is about the caching, and file systems also are about the caching. So we will see why modern processors are really bad when we have high latencies. And then moving forward, how other UNIX type of systems manage to overcome this problem of caching, in particular Solaris 10 page cache and modern Linux page cache, how it works. And from the other side, what users would like to do from user space, which means how users would like to read data to the file system, to the storage medium, what kind of requirements do they have. And then we will move briefly to some code fragments, basically how you can go to our dummy.fs and plug into the kernel interfaces in order to use page cache, for example, for read write, how to do mmap. Small disclaimer: we won't have as much code as previous time because you will see that Linux kernel provides a lot of different interfaces how to use the page cache. So most of the code is already written, and some code that is required, basically required to plug to the interfaces, but also it's sometimes can be a little bit longer. So we will talk briefly what needs to be done in this case. So this is a repetition from the previous talk, why people would not be interested in file systems. So why some people may not be interested in learning file systems. So first thing is writing file systems is quite time consuming. So from some conversation with some managers, few people from community get some overall estimate like ZFS, which is some file system written in released in 2004, I think 2004, that it took them approximately 10 years in man hours to develop the file system, because file system need to be stable, need to be reliable. So it's big effort. So probably your company would not be interested in writing its own file system unless they have some free resources from 10 years. And just few production-ready file systems, many abandoned and not truly maintained. So this is another problem we have in Linux. Extended file system in a few versions, XFS, Btrfs, ZFS sometimes, for example, on Ubuntu. But actually, this is quite that we have, and those are quite stable, reliable. So why you would like to move to something else? And also, currently, file systems are considered as passe, so everyone would like to use object stores, NoSQL databases, stuff like that. So why would I be interested in file systems? But from the other side, my motivation for this talk is basically I would like to address some specific education gap. So basically, if you are working on some complex environments, sometimes you may need to know what is going on inside the file system. Sometimes you may want to, for example, get two different file systems and run your database on it, do some profiling, understand where are those differences. Maybe copy and write file system would be better for you, maybe not. And if you will start, from simple tutorials or for simple information inside the books, there is a lot of stuff at the beginning. What are the structures? Then there is long time, nothing. And then there is a source code for file systems. So basically how you would go from the part when you understand, okay, so we have those structures to actually how this stuff is actually working under the hood. So basically it's kind of long way, and this presentation is trying to at least address part of this gap, of course, not everything. And another thing, solving other complicated problems. Memory management is considered as a quite difficult topic, and I fully agree with that. It took a while for people to understand how these things works and how this work for file systems, how this work for processes, why things work in that way. Also, many things changing so quickly, especially in Linux world. Storage stack usually is considered as a bottleneck for different applications. So usually when people have bottleneck, they think, oh, probably my storage screwed up. So maybe we can get something quicker. Maybe we can move to Flash. Maybe we can move to something else in order to mitigate that. But usually those kind of problems need much more investigation and understanding of the internals. Yeah, so one other comment in terms of passe things. So I do not really like the CEO of Oracle, but one time he had like a conversation about new technologies, and his statement, I really remember his statement, he says, IT industry is the only industry that I really know which is more fashion driven than women fashion. So we have also something in our industry, like people used to switch to new things quickly because they wanted to get new stuff and run on it. But sometimes old proper storage or old proper stacks were developed in the way how they are because people had some experience, solve some problems. And then, for example, moving to object stores, stuff like Ceph, people still have, again, the same problem. For example, problems with the snapshots and really slow performance of Ceph snapshots, for example. That was one thing that I met when I started doing some work on the Ceph. This was fixed after some time, but same problem as we had in file systems. Okay, so starting first of all with really 10,000 feet overview of virtual memory in Unix. So from commentary of 6th edition of Unix from Linson from 77, he described the way how processes are sharing the memory in Unix in the sentence. Unix, like all time-sharing systems and some multi-program system, use program swapping, also called rolling in, rolling out, to share the limited resources of the main physical memory among the several processes. So this fact was then in 90s described by another good Unix researcher as a way how in Stone Age Unix managed the virtual memory. So basically you have few processes. The processes have some contiguous memory called segments. And this memory was basically, the kernel was able to write the memory to the backing device and bringing back the new process. So basically, every time when we were doing scheduling, because the memory was so limited, we basically need to write the whole process to the backing device, bring back the new process from the swap device. So the virtual memory is kind of high-level abstraction, and we still use similar concepts. Some things change, but we still have central processing unit, which is connected to the fast RAM, which is also, and also a storage device, which is considered as a really low device. And the foundation is the same. We are not able to feed the whole data that we need in the RAM. We need to move data back and forward. But the way how this was done changed over the years. So first important change in virtual memory management in still 70s was introducing the paging. So basically, I think this is a really basic concept for everyone, but just briefly, we can divide the whole physical memory to the pages. Every page has its own number. Different virtual address spaces, different processes can basically point to different pages. So for example, we can easily share memory. A 0 is shared between those virtual processes. We can do some cheating on the processes. For example, if you allocate 1 gigabit file with only zeros, you can point all pages to one page, which is basically containing zeros. And then you will just lose, instead of 1 gigabit of the data, just 4K in your memory. So all of those different things can be done because of the paging. So paging has this advantage over the swapping, that you have less granularity, you can move things quicker, but from the other side, it's complicated, it requires some hardware support. But this is the way how newer systems started to work, by introducing the paging. In the 70s, there was some research about different policy for the pages. So fetching policy, when do we fetch the policy? When do we fetch the page from the memory, from the disk to the memory? Placement, where exactly we put those pages? Replacement policy, how do we make sure that we do not swap out the pages that are most recently used, that are used by different processes, but we will move just the pages that are old and not recently used. Right now, we used to call those three guys just by paging policy, because of the complexity, things were merged. There was some research. For example, right now in Linux, we have two lists of the pages. One list is the list of the pages that were just touched once, because people realized that pages that were touched just once are more likely to be swapped out to the backing device than pages that were touched a few times. Because if you are touching page once, probably you are doing some scan, reading some big file, and probably you are not needing this data anymore. So for example, why not swap them out? But also another thing that is done in the page management, if you swap the page, so page can be promoted from unused list to used list if it's touched twice. But if we swap out the page, which was not used, we still keep for the moment the reference for this page. So for example, if someone else will touch this page again, we will see like, oh, this page should be here, but we don't have this page because we think like we swapped them out. So let's bring it back from the backing device, and do not put this to the unused list or list where we store the pages which are touched once, but we did mistake, let's put it to recently used page, to recently used list, because this page probably most likely will be touched several times. So those policies become a little bit more like heuristic or guessing, if you will, but it shows you the complexity of the problem of managing the pages by virtual memory. Demand paging. So demand paging is another technique of virtual memory introduced in '78 with VX11. This was the first DEC mainframe which has 32-bit address space. And it provides demand paging, which require hardware support to maintain the page table inside the processor. After 80s, all UNIX started using the demand paging instead of swapping techniques. So it shows you like till 80s, people still were doing the swapping about the whole processes because it was easier. And after that, once the hardware also become a little bit better and modern, provides us more features, we basically were able to introduce more complex solutions. We also introduced the memory fault, which basically means if we refer to some address which is not in the memory, we need to load the page from the secondary device. So we have two page faults, minor page fault and minor page fault. Minor page fault is a fault when basically we do not need to do this IO. So because we have pages, for example, if we touch something and we don't have this page, but maybe some other process does have this page, so maybe you can just reference the other page. Or maybe this page was prefetched and it's already in memory, but we need to find it. But it's not in the page table, so we need to find it. Major is for file systems, is for swapping, for other things, basically, when we need to go back all the way down to the disk and find the page. Okay, so next thing. Computing is all about the caching. So my Intel CPU can execute about roughly 50 billion instructions per second, of course, unless it takes a cache miss. DRAM, 2 orders of magnitude less in terms of cache lines per second. SSD, again, 3 orders of magnitude less for pages per second. So basically, this is kind of the problem that was always there. And if you take a look on some older hardware, PDP-11 for 100,000 instructions per second, but the memory was quite comparison faster than today memory. So it was the same order of magnitude. RK05 drive 4,000 pages per second, so just 2 orders of magnitude less than the processor. But if we will take a look on this chart, and this chart is of course to 2010, we will see like this gap is still widening. Of course, right now processors stop speed up as they used to. So basically, there is we are reaching some barrier. So people are putting more processors because processors are not getting faster. And memory is not really getting much faster, but storage, for example, is getting faster because we have a lot of. First of all, we have the flash devices. We have devices that are connected by new PCI link. So basically, you are able to touch the persistent data almost in the speed of the memory. So this picture will change in the future at some point. But still, we will have really amazingly fast processor, slower memory, and slower back storage device, which may or may not reach at some point the speed of the memory. So to give some examples why those latencies are really good. So some numbers that which programmers should know, or at least that was the title of those numbers on GitHub, and this maintain this page by the community to keep it up to date. So we see the same thing. Stuff on the processor in order of nanoseconds, L1, cache reference, half of nanosecond, L2, 7 nanoseconds, main memory reference, 100 nanoseconds, order of magnitude. SSD random read, 3 orders of magnitude, 150 microsecond. Read sequentially, same order. And then we are going to HDD disks. So we are going, again, we are going one order of magnitude slower in reading. The disk SIG is incredibly slow. Reading from the disk is even slower. So someone can think, okay, so 20 milliseconds is not too bad, right? You cannot distinguish 20 milliseconds from 200 microseconds in blink of the eye. But from the other side, if we will unload those numbers by billion, we can compare one L1 cache reference by 1 heartbeat, 0.5 second. L2 reference is 7 seconds, so it's already like dispatching espresso in the coffee machine. Main memory reference, 100 seconds, so it's like doing toast, like a full sandwich. SSD, really weak. So you can imagine yourself working when you need to do some operation, which basically takes you a week, and you need to do this in order to keep up with your work. So you can, I don't know, if someone had this bad experience on going to some institution on Friday evening and they are just closing the doors between the phase and saying like, look, we'll just serve you in Monday, next Monday. So it's long delay from people perspective, and from processor perspective, it's something that we do whenever we are reading from the disk. So what's the general caching problem? We have our process, we have our files. Every file has its own memory. Some pages may be already loaded, some pages are not loaded. And in the exercises, we would like to make this as fast as possible. We pay a lot for the processor, and we do not want to waste too many cycles during, just waiting for the device. So we don't want our processor to wait those 2 days to go back to SSD, or even a week to go back. Or this was even almost 8 months to go to the HDD drive and load the pages. So how we can solve this problem? So the first thing that we may think, okay, why do not load everything from backing device till the file, because we need those pages, right? Most likely we will have some of those pages. We do not want to risk, so how do not fetch everything from the disk to the memory? And we should be lucky, but we have many files, so we cannot probably keep them all in the memory. And from the other side, this is kind of the approach that looks similar to the swapping from one of the first slides. Like we just fetch everything for the process, then we are doing operations. Then when another process will come, and we have thousands of processes, we need again to load the pages. So we will need to swap out. The process itself. But this is kind of general problem, and many operating systems attach this problem in a similar way. So if we will take a look on Solaris, this is on Solaris 10. What we have on Solaris 10? We have, again, file system, VFS, which basically was connected to vnode. Vnode is inode, as you may remember from the previous presentation. So inode is on Linux, vnode is on Solaris, and then system V type of operating systems. Every vnode has its own page list. So basically all the pages that are connected to the file, because we have to represent the file, are in the linked list. Also, vnode points to log device from which we do fetch the files. Every page on this page, every page structure, it's not every page, has a pointer to the page cache, to the bucket of the page cache. And basically, the Solaris page cache is a hash table where the key is vnode and offset. So we need to store the pages of given addresses, or we need to store per file the whole pages. So basically, we have many different pages as we are moving forward with address space of our file. So we need to have efficient way to find those pages, because we need to reference those pages. We may need to put them on the blocking device. Also, there is a free list of pages. So Solaris also maintain the free list of the pages, which basically if the page is not used, we put them to the free list. And basically, when someone needs new pages, we can put those pages to the cache. So we have one global hash table as a page cache for the whole operating system, which gives us some natural problem when we think about the scalability of this solution. So take a look how Linux do the same thing. So back before 2.6, in Linux, we also had similar structure as Solaris. So we do have a page hash table for one global hash table for maintaining the pages. But after some time, people realized that there are some better structures, basically to finding the element from the address range. And the trees are usually really good with those kind of operations. So why do not use tree? And here there's a radix tree. So we have Superblock, which has connected inodes to it. Every inode has its own address space. So address space is an object which keep reference to the page cache. So the Linux page cache is not a hash table right now, it's a radix tree. And so we have one page cache per one file. But we do not copy the pages. Pages are just directly linked by nodes of the radix tree. We have, of course, backing device. We need to keep sync of radix tree versus backing device. So this is kind of complicated problem, but also is well tested and is super stable. It's really stable, I should say. Yeah. So moving to different dimension of the problem. As a user, so we talk how the virtual memory management see the memory, what kind of different structures do we have, and from the other side, what kind of operations do users would like to do in the file system. So we have storage stack, it's the same as I showed earlier. So just brief overview. We have user space application. We have some data from in our application which we would like to write to the storage. Way down we have VFS, virtual file system, page cache in the middle. We have file system, volume manager, which I do not spend too much time about talking what the volume manager is, but you can think about this layer like we need some drive to write our IOs to the storage device anyway. So we also may need some kind of scheduler for IO, something intelligent, basically do those operations. But as a user, we can have different patterns, how we would like to access our storage media. So we have buffered IO, really quickly. In buffered IO, we assume that we have application doing frequent read-write. It's okay for application if we do not write directly to the storage, we just write to the page cache. So basically, this is write back pattern for cache, which basically you write data to the cache, and then after some time, cache will write back the data to the storage device. And we are okay if something will go wrong and we will be out of it. That's kind of design decision, because we would like to basically have the performance. From the other side, as a database, people may think, okay, I would need to make sure that my IO actually went all the way down to the storage. So this is where we have synchronous IO. So basically, the hot path is file system. We write to the file system write to storage device, and then we flash the data to the cache. Because even if this is synchronous IO, when you are doing read, you don't want again to spend this 2 days if this is SSD, or from processor perspective, 6 months if this is HDD to get back your data. So we are kind of cheating and push the data anywhere to the page cache. So then when someone is reading the data, is able to basically reach them from the page cache. And because page cache and storage device are in sync, we do not have any problem. But most of the people think that they know the best, what is the best for their application. So they would like to do caching public their own. So if I'm an application like database, I probably have better guess than the kernel when I should go with the data to the cache and what user will like to fetch from the cache. And then I'm just doing those writes to the storage device frequently. So I would like to do this every period of time to do some kind of tag, some kind of checkpoint when I will have the storage device in sync with my data. So we have direct IO. Basically, direct IO go all the way down the file system. We do not involve here the page cache. We pull the data to the storage device, but this is not entirely true, again, because the whole thing is all displayed. So sometimes you can also have situation when you have your application which is doing direct IO and another application which is doing some buffer IO for the same file, not in this case. So fortunately, kernel has its own way to do direct IO. So it should make sure that before you write the data to the cache, those pages will be flashed out to the disk. But many years ago, it wasn't the case. So there was a lot of discussion in the kernel community about direct IO. There was even some hard statements from Linus towards like people should not do direct IO. We as a kernel know best what is the best for your hardware. If you are doing direct IO, basically you don't need the kernel. Maybe you can just write environmental stuff like that. But that was something that was kind of industry standard. So direct IO was introduced as a POSIX standard. So we needed this in Linux. So we need to make it work on Linux somehow. The last pattern, memory map IO. So application may also think, okay, so I would like to use, I would like to have my memory on my side, like see my memory, but use the page cache. I don't want to do the copy of the data, so I would like to have references for this memory in my user space, but I will let Linux page cache or page cache of operating system to make those synchronization by its own. So we have the memory. It can be anonymous memory. It can be a file, and we are talking mainly about files because we are writing file system for Linux. So we can write the file and make sure that this file will be in sync. Of course, this write back is not the critical part. So we are just doing operations on the page cache, and after some time, the page is doing synchronization by its own. And in order to do that, we need to do a map system call. And once we're done with some part of the memory, we need to do a map of the region. The last thing from theory, I know that you probably are already bored at this point, but how the page cache interact with storage device. So we put the pages. So basically, radix tree, we have left the pages. We need to put them to the storage device or bring them back. So we have the offset. We have the file inode. So basically, we can just do the put page, write it back to the storage. We can get the page if we need to load something. And that is a kind of high-level interface for page cache. Okay, so moving to our file system, we will take a look how those primitives, how those things can be implemented, how we can plug in to the kernel interfaces in order to, first of all, make sure that our IO we will be able to serve buffered IO over synchronous IO. And if probably not many people remember, but in previous talk, the way how we do IO was basically going all the way down to the disk, reading the buffer cache from the disk, and then modifying the structure, writing them back to the disk. So basically, it was really inefficient because every time we go, read from the disk, find what we need to modify, write it back. And even if we use buffered cache, so basically I introduced buffered cache, but I didn't explain what is it. We have two caches in Linux. We have page cache, which basically is radix tree, and we have also buffered cache, which is kind of the buffer for the disk. Back in the days, in the 90s, there were just two different caches, so there was kind of synchronization protocols between them. Right now, they are mapping just to the same pages. So basically, all pages that you have in your page cache, you also have in your buffered cache. So basically, they are always in sync. And it basically helps you whenever you're doing disk IO because you can just, lay out those buffers with the pages and then after some time flash them to the storage media. So we would like to use those interfaces in our dummy file system. We want to also to make sure that direct IO works and omit page cache, and see how we can support mmap and mmap. I'm running out of battery, so hopefully we should go to the end. First thing, mmap. So basically, the way how we can plug into the mmap is really simple. So every file has its own file operations inside the kernel. So whenever we create a file in our file system, we inherit those operations. So we need to provide the method mmap, which is pointer to the function which basically have a file and virtual memory area struct. And because this is a generic problem, we can just easily plug to generic file mmap with the file and virtual memory. And what this generic function really does is basically get the segment of virtual memory and put those three operations on as a virtual memory operation. So basically, every time when any of the pages from VMA will have a fault, we will basically read them from. We will basically trigger the page fault. We will read them from the disk and put them to the radix tree. We have MapPages, which is a method that basically gives you the pages and put them to the radix tree on proper offset. Page mkwrite. This is the method where basically we have read-only memory, and we would like to do the read-only memory writable. So you can imagine the case that I mentioned previously, like we have two processes that point to the same page. And we just open those files. So basically, currently, why do I need to have two pages? I can just point those two pointers to the same page. So those can just read the same page, so I will save the space. But what will happen if some process would like to write to this memory and it open it with write permission? Basically, under the hood, we will do the copy on write. So we will trigger this event because we are changing the permission. We will move the data to another page. We will allow another process to write to this memory, and depending how the applications are using those files, basically continue. So it may be basically flashed to a different file. It may be flashed to the same file, and then we need to do the same. Everything depends how user space will do that. Next thing about the reading writing through the page cache. So again, this is generic problem. So we have generic interfaces in the kernel. We can just plug in to generic interfaces, which are, again, for the file read iteration, which basically are stub for generic file read iterate and generic file write iterate. So those two methods under the hood are doing one thing. So basically, we check if we would like to write the file immediately or not. If we do want to write, if we can wait, if we don't have to wait, sorry. If we don't have to wait, find if the page is in the range. If it's not in the range, we need to return again because probably this page wasn't yet loaded. If we need to wait, we will use the methods. We basically will find the pages, write them, and wait, and then return. And in our case, we'll use another generic method, which basically will do the read or write, depending which operation we are triggering. And so this is still kind of generic code, which is common for all file systems. So extended file system, XFS, we are all using under the hood generic file read. And basically, there are some other parts, like currently there's a lot of hash defined with DAX and other things, which after some point probably will be also merged to those generic interfaces. But right now there is still some kind of debate what we should do for the case when we have a persistent memory, when we don't need to write the data to the disk because the memory is persistent. But we need a few more things. We cannot just rely on the generic stuff. So we need to provide the methods in order to reading, writing the pages, and reading, writing a single page, multiple pages, write begin, so write end. So basically those region writes and bmap, which bmap is actually the method which gives you, given the page, will give you the offset of this page inside the file. So it will go to the radix tree, find the page, calculate the offset, bring you back the offset. So again, we have generic methods, which is great. So we have mpage, read page, write page. So those are just generic things. But there's one thing that is file system specific. We need to specify how the kernel will get the particular block from the storage device. So basically, we have this radix tree. We can calculate the offset easily. Those things are still in the memory, so we are just traversing the memory. But when something is not in the memory, we need to bring this back from the file system and put it to the radix tree. So we will call get block. So the get block will gives you the block in the given offset for inode, and this is a file system specific thing. So all the file systems are using those general interfaces, but they have different internals. So basically, get block method is different. So going to the get block, as I said, we have inode, iblock, index, buffer head, which basically is a result. So basically, we would like to map the block that we found from the disk to this buffer head, which is basically buffer cache for the file. And we also have a flag if we would like to do the create the blocks, if we need to create the blocks, or we can say like those blocks should be on the disk, so do not create them. So the simple implementation of this function, basically we need to calculate how many blocks do we have in the page. So we need to do some bit shifting. We have another method which is much more complicated, get blocks. We basically get this number of max blocks which we would like to get. It's return also the number of the blocks, and also provides you some information if there is any error, if we didn't find anything, or we successfully map amount of different blocks. And then when we have the result, we basically do the operation of the buffer head. So we need to map buffer head because we can also have some data in the range that are, for example, not in one page, but are in the middle of the pages. So we may need to get two pages, link them together, because buffer head is just structure similar to scatter gathering. Basically, you have a pointer to the data, you have a pointer to the next structure. We also have some logic if we create new buffers or if we hit the boundary. So basically, if we write more that we really require, we need to do the truncate. Okay, so I didn't provide the full implementation of get block because this will be really big and heavy, but basically, the function will contain few elements. First of all, we will iterate through all extents and see if our blocks are inside the extents. So basically, if the data that we are reading are inside one of those extents that we have. If yes, we can just simply return this data. If not, we need to also check if basically the create, if someone called the function set create. So if we set create, we also may need to allocate those blocks, put them to the proper branch, which basically is file system specific. And currently, WFS does not support indirect files, indirect inodes. So basically, we have just few direct pointers to the extents. So basically, we would like to just put another extent on our inode. And if we reach out the count, if we reach on the boundary, we would like also to set up the flag to the previous method to make sure that it will cut off the buffer because we just wanted to have this region, this particular region, and put this particular region to the page cache. And last but not least, direct IO. This is again the common operation for all file systems. So again, every other modern file system in Linux, maybe except ZFS, because ZFS does not support direct IO, will use basically block that direct IO. So someone may ask, why would you use the methods that we had previously, this read and write? So basically, we can get from IO the flags. Do we need to read or do we need to write? And then basically plug into the existing functions that we have to do read, do write directly to the disk. However, as I said earlier, the problem with that is we may run out of sync with the page cache. So we can do this, but if someone else will basically run something on different process on the same inode, basically we can run into the trouble. And also this is the default way how we should interact with direct IO. So why do not understand how other file systems are doing this? Again, this is a generic method, but also it requires us to provide methods to give us a block. So we need, for all of those generic methods, basically we need to provide a file system specific method to fetch actually blocks from the disks. Okay, so here we have some resources that I used for the presentation. Some of them are the same. Leon's commentary of 6th edition, Solaris internals, Uresh, so those are kind of old books, but to be honest, when you are reading the code from the kernel and you don't know some things, sometimes it's good to get some old book, see the evolution, how this problem was solved previously, how this evolution basically evolved over the time, and after that you will be able basically to understand better design decisions and understand why people implement this in that way. I use for my examples XT2 and UFS Linux source code. There is a GitHub for dummy-fs. The current methods are not on the GitHub. I will need to brush them a little bit better and submit them, but I'll probably do this during the week. So thank you very much for your attention. And if you have any question, let me know right now. Or there's also my Twitter link. You can just tweet me. Thanks. Any questions?
How does sequencing fragments take place in memory? I didn't really pick it up from the code there. I probably missed it again.
Oh yeah. So the question is how the VM segments or how the pages are picked up from the
how the pages are picked up, like the order in which they're picked up.
Mm-hmm. So basically, we would like to map. So we know that our files, if they are not sparse, if they don't have the loops inside, if they don't have holes inside, they should be easy to map like in linear fashion to some kind of address space. If you have holes, basically you need to put more logic, but you can divide this address space to the pages. You know that your page is 4K. So basically, whenever you need to pick up the page, you need to get an offset. So you need to know on which offset you do the read. So for example, if you are doing the read, you are doing LSIG 2K, and then you want to read 2K from the memory. So you are still in the first page. So you will load, depending on your file system, you can load, for example, 4 blocks if your block size on file system is 512. If your block size is 4K, you can load just 1 block, put this to the memory, and then your data is here on this offset. So because every, I show this on, sorry, it's a bit slow. Oops. It's stuck. Anyway, basically, you have the pages which are associated with inode, So every inode has its own inode on the disk. So file system is responsible for going all the way down and basically finding the inode on the disk and then doing this mapping. And because you can have, I cannot see myself when I'm talking. And basically, whenever you know that you're going to the disk, you have different layout of your file. So it is allocated in extents, in blocks. So, but this is kind of logical sequence. So basically, you are going through the extents, and you know that those extents should be kind of, even if they are separate on the disk, because you allocate part of the extents here, part of the extent there. This is 2K, this is another 2K. If you are combining them together, you have 4K. So you are fetching those two segments and putting them to the page.
And they're located by the referencing, the low-level referencing.
Yes, so every inode has its own extent list. So basically on every extent, you know, start of the, so if you have extent type file system, if you have block-based file system, you reference just blocks. So you know exactly what blocks are in your file. If you have extents, you reference your extent starts at block 10 and has 10 blocks. So if your block size of file system is 512, that means you have 5K of the space. Anything else? Okay, thank you very much for your attention.